Distinguished guests, esteemed colleague, good morning. The title of my presentation today is A Comparative Study of Vortex Identification Method in the Oil Field of a Commercial Vehicle Gearbox. My name is Ren Yi from Jilin University. On behalf of my superior, Professor Chen Boson, I will be delivering this presentation. Professor Vortex holds a doctoral degree in engineering and currently serves as a professor and doctoral supervisor at School of Mechanical and Aerospace Engineering Jilin University. As the academic leader of the research team, Professor Chai has established well-defined research programs and achieved outstanding results. He has set over 12 research projects as the principal investigator, including national-level, clinical, and industry collaborative initiatives. Notable projects include the General Program of the National Nature Science Foundation of China and the Outstanding Young Foundation of Jilin Province. His primary research efforts are concentrated in three main areas. The first is research on the bionic design of fluid machinery and hydraulic and aerophobic characteristics. The second is fluid machinery design and test machinery technology. The second is mechanical transmission, hydraulic transmission, bionics. Through systematic research efforts, Professor Chai has published 25 papers indexed by SCILEI, obtained 2 authorized national invitation patients, and received 2 Premical Science and Technology Awards. In recognition of his outstanding research performance, he, he was selected for the key stage of Jilin University's Lixin Outstanding Young Teacher Training Program. In the field of the fluid machinery research, his team has established a comprehensive system encompassing advanced research methodologies such as CFD numerical simulation and PIV flow field visualization, forming a distinguished feature in the study of vortex, vortex computation mechanism in hydraulic competence. My name is Ren Yi. I am currently a master's candidate in mechanical engineering at Jilin University. Under the supervision of Professor Boson Chai, he conducts research at the emerging young research within the team. My primary research focuses on the following 3 areas. The first is process identification and effectively all the calculation of cavitation in the torture converter. The second is thermal modeling and validation of gear transmission system using FC. The second is particle physics coupling analysis of a commercial vehicle gear transmission system. My presentation is structured into 4 main parts. First, I will begin with the research background. Then, I will elaborate on the numerical method employed, with the specific focus on the crucial model validation process. The second part, which constitutes the core of this presentation, will provide an in-depth consideration of several vortex identification methods. Finally, I will conclude with the main finding of this study. First, let's consider the research background. As shown in Figure 1.1, the commercial vehicle gearbox is a core component of the vehicle transmission system. Figures 1.2 and 1.3 illustrate its internal gear transmission and oil changing processes. Gear transmission adjusts torque and speed to meet vehicle demands, while the internal lubricating flow fields constitute a complex system. This system is characterized by its unsteady multi-scale nature, including a gas-liquid two-phase mixture and complex vortex structures. Consequently, precise access of the internal flow field via computational fluid dynamics is crucial for optimizing the gearbox's lubrication and cooling design. The objective of this study is to identify and characterize these complex vortex structures more clearly and accurately. To achieve high-fidelity simulation, the offset grid technique was employed to handle the rotational motion of the gears. The computational domain was divided into two parts. A component zone contains the gears, and an external background zone. The grids for these two regions were generated independently. During the calculation, data is transferred between the foreground grid and the background grid. For each active grid cell, a neighboring donor cell is affiliated, and its fluxes computed based on the information from the donor cell. This approach effectively prevents grid distortion and accurately simulates the large-scale motion of the gears. The selection of an appropriate turbulence model is critical for simulation accuracy. To identify the most suitable model, a single-gear oil changing test batch was established for validation. The test apparatus includes a motor, a torque sensor, a gearbox, and an electrical control system. Correspondingly, a computational model for single-gear oil changing as illustrated in Figure 2.5 was developed. A systematic comparison was conducted among three widely used turbulence models: realizable K epsilon, RGK epsilon, and SSTK omega, evaluating this accuracy in predicting changing torque loss and reconstructing the oil distribution. Figure 2.6 presents a comparison of the oil distribution between experiment and simulation results, while Figure 2.7 provides a quantitative comparison of the changing torque loss. In terms of oil distribution, both RGK epsilon and RSSTK omega models outperforms the reliable K-epsilon model in capturing follow patterns and oil-air interface behavior. More importantly, quantitative results of the total loss demonstrate that the prediction of the RGK epsilon model agree most closely with the experimental measurements, exhibiting the smallest mean error. Consequently, the RGK epsilon model was selected for the next simulation. Following the determination of the turbulence model, a high-quality grid system was constructed. This was achieved by integrating an unstructured foreground mesh with an structured background mesh. Figure 2.8 displays the gear oil mixing model, while Figure 2.9 illustrates the foreground mesh, background mesh, and the overall computational domain. To accurately resolve the near wall follow a boundary layer mesh was implemented on the gear surface with an internal layer thickness of 0.0015 meters and a growth rate of 2. Furthermore, local mesh refinement was applied to key regions of the fault domain, including the gear size, tool surface, and shaft areas, as depicted in Figure 2.10 to ensure the accuracy and reliability of the computational results. Figure 2.11 presents the grid independence, which confirms that the simulation results are minimally influenced by the grid resolution. The numerical simulations were performed using access fluent, employing the overset grid technique and the volume of field particle phase model. The acceleration due to gravity was specified and the RGK epsilon model was selected. To simulate realistic thermal effects, a user-defined function was utilized to dynamically apply a heat flux at the gear meshing point. Furthermore, as outlined in Figure 2.12, the oil's properties, including density, speed, thermal conductivity, and viscosity, were defined as a function of temperature. This approach enhances the physical validity of the simulation by more closely representing actual operating conditions. We now proceed to the core section of this presentation, a comparative analysis of vortex identification method. We begin with the single gear operating condition. Three vortex identification method was selected for compression, calculation, omega method, and omega mutex method. Figure 3.1 illustrates the three-dimensional vortex structure identified by these different methods at rotational speeds of 500, 1500, and 2500 revolutions per minute. It is visually apparent that morphology and the detail of the results obtained from the different methods exhibit significant difference. The vortex identification results exhibit a strong dependence on the selected threshold value. We first present the performance of three methods under different thresholds at rotational speed of 500. For given method, as the threshold value varies, the identified vortex structures change significantly, ranging from sparse and large-scale to progressively thinner and more detailed. The objective is to determine an optimal threshold that adequately captures the primary vortex structure while maintaining clarity. This comparison illustrates the results when the rotational speed is increased to 1500. As the speed rises, the vortex structure becomes more complex. It can be observed that both the calculation and the homing method are susceptible to losing thinner vortex or misidentifying shear layer as vortex when an inappropriate threshold threshold is selected. In contrast, the Vortex method applies to demonstrate superior coherence across different threshold values. Finally, the compression at the maximum speed of 2500 is presented under high-speed computation. The flow field exhibits the highest complexity, posing the greatest challenge to vortex and fiction methods. At this stage, selecting an appropriate threshold becomes particularly critical. An improper threshold may lead to a completed misinterpretation of the flow phenomenon in key regions such as the gear meshing point. Based on extensive lecture review and threshold experimentation, an optimal threshold was determined for each method to accurately represent the three-dimensional vortex structure. Table 1 summarizes the explored threshold ranges and the final selected values. Figure 3.5 subsequently presents the three-dimensional vortices identified by each method under their respective optimal threshold condition, allowing for a directed comparison of comparative on a relative equitable basis. A longitudinal compression across the three rotational speed reveals a consistent overall trend in the vortex structure. The fact within the whole full flow passage of the gearbox by the Q-creation omega and omega lutex method. As the rotational speed rises, the vortex structure becomes more widespread and morphologically complex. Other methods capture the primary vortex co-location and extend with general agreement and distribution patterns of the large-scale vortex structure level. A lateral comparison of methods, however, highlights significant differences in gear meshing point. Both the Q-creation and the omega method depicted lower oil volatility in this critical region, fail to accurately reflect the high-speed oil flow generated by the shear on the gear-to surface. Furthermore, the oil distribution on the gear surface appears sparse and discontinuous using these methods, suggesting a particle mass response of the oil film set. In contrast, the omega-lutex method discriminates higher oil facilities in the meshing point, which aligns more closely with expected physical conditions. It also yields a more continuous and uniform oil distribution, providing a more accurate and reliable characterization of the lubrication state. We paid particular attention to the detailed vortex structure in the high-speed gear meshing point region, where the flow exhibits intense shear characteristics. A qualitative analysis of the vortex structure reconstruction on the two surfaces within the gear meshing pair, as shown in the gear meshing point region of Figure 3.6, reveals notable difference in the performance of the three vortex identification methods, further confirming the supporting of the omega test method in complex flow regions. The results identified by the calculation show a disorganized velocity distribution with fragmented and poorly continuous vortex structures. The omega method shows some improvement, able to roughly depict the general distribution trend of the vortex, but its capability to capture spin, scale, and big vortex remains limited, resulting in incomplete vortex structure at the matching point. In contrast, the omega-text method produces vortex structure with clear boundaries, accurately reconstructing the spatial distribution and morphological features of the vortex course near the gear matching points. It demonstrates strong reliability in identifying when-scale vortex and maintaining structural coherence. Based on the comprehensive analysis presented above, we arrived at the following three key conclusions. The first is, compared to the Q equation, which is sensitive to thresholds, and the omega method which is weak in small-scale identification, the omega text performs best in multiple-scale vortex identification. The second is, compared to the intermittent Q equation and the omega method with insufficient detail, omega text can clearly and coherently reconstruct the completed oil film morphology. The second is, compared to the Q equation and the omega method, omega text has the highest accuracy in characterizing strong shear flows and the greatest engineering value. Thank you for your listening.